Okay, in this video we're going to be talking about inverses of linear maps. So we finished this section by considering how to represent the inverse of a linear map. And we know that we've been associating linear maps with matrices, so it's quite natural to infer that the inverse of a linear map will be represented by the inverse of the corresponding matrix. So we'll see how that works in this section. So first, recall some things about inverses. Let pi be the projection map. Pi is going from R3 to R2. So what pi does is it takes a three-dimensional vector and it strips off the third dimension and just gives me the first two components of the vector. On the other hand, I can talk about the embedding map, which takes R2 and identifies it with the xy plane in R3. Okay, so notice the difference here. xy is a self-contained space. Here we're considering it as a subspace of R3. Now, if I take the composition of pi following I, so I take I first and then pi, what's going on here? Well, I have xy. I'm identifying that with a point in three-dimensional space, and then I'm taking the projection. So I could kind of write that this way. Here I have xy, this is R2, and I'm identifying that with the xy plane in three-dimensional space. So I'm identifying it with this plane here. If I have x, y, z here. So I'm identifying points here with the points in here. And then if I take the projection of this point in three-dimensional space, well, it just simply takes me back to the same xy. Okay, because I'm only considering the xy coordinates of this point. So in fact, if I take I and then pi, I have an inverse relationship. So we say that I is a right inverse of pi. It's called a right inverse because I is here is to the right of pi. Okay? Or we can say pi is a left inverse of I. However, if we do composition in the other order, I compose pi does not give the identity map. Okay, well, I compose pi, so what does that mean? Let's look at this picture here. I have x, y, z again. If I have a point x, y, z here, now the projection map will take me down to the xy plane, and it will only give me the x and y coordinates. But then if I consider the embedding map, the image of the embedding map will simply be this point here in three-dimensional space. And we can see that in this particular example, if I have 0, 0, 1, that's this point here. If I do the projection, that takes me down to here. That's going to take me to 0, 0 because I only consider the first two components. And if I consider the xy plane as within R3, that identifies with 0, 0, 0. So here we can see that pi followed by I does not give the identity map. Okay, pi followed by I is represented as I composed pi. Okay, so pi does not have a left inverse. For if f were to be a left inverse of pi, we would have x, y, z goes to x, y goes to x, y, z for all the infinite many z's. The point is that pi is not one-to-one, so there's no possible way that we can get inverse for pi on the left. Okay, so a function can have a right inverse but no left inverse, or vice versa. A function can also fail to have an inverse on either side. One example is the zero transformation on R2. If everything maps to 0, then certainly there's no inverse to that, either on the left or on the right. I can show that a little more explicitly here. Suppose I write the zero transformation here. Now a left inverse would be a transformation that takes 0, 0 back to the original xy here. It's a little confusing because we're saying this, here, let's call this the zero transformation here. And we'll call this the inverse, I'll call this f. Here, f would be a left inverse of z. It seems confusing because here f is on the right of z. But when you do the composition, this would be f composed z. But clearly, there's no function f that can make this work because everything is smushed down to 0, 0. There's no mapping that can be defined that maps 0, 0 magically to any possible xy that gets mapped to 0, 0. So there's no possible way to find a function that inverts this 0 function. On the other hand, if I have the 0 map, then any point in R2 gets mapped to 0, 0. And there's no way to map an arbitrary xy in some fashion such that this arbitrary vector gets mapped back to the original xy, because everything gets mapped to 0, 0. So this is my 0 mapping. Here's my f. There's no possible way to find a f that makes this diagram work. Okay, so that shows that the 0 transformation on R2 has neither left inverse nor right inverse. Now, some functions have two-sided inverses. Another function that is the inverse both on the left and from the right. For instance, if I take the transformation v to 2v, and here it's not clearly what the vector space is. In fact, for any vector space, such a mapping has a two-sided inverse. V goes to 1/2 v. And you can verify that directly, that if you take this transformation and then this transformation, you end up with the original v. The appendix shows that a function has a two-sided inverse if and only if it is both 1 to 1 and onto. That's a general fact about functions. You may have seen that in your discrete math class or somewhere else, but it's certainly a general fact on any kind of function, linear or not. The appendix also shows that if a function f has a two-sided inverse, then it is unique. So we can't have two different inverses for the same function. So we can talk about the inverse and write it as f inverse. Okay, so if you're not familiar with those things, I invite you to look at the appendix. You'll certainly see this again in abstract algebra class. In addition, recall that we have shown in figure 2.2.20 that if a linear map has a two-sided inverse, then that inverse is also linear. Okay, let me show you that theorem. It's here on page 199, and it says that if we have a linear map, then H is 1 to 1, then H has an inverse from its range, not codomain, from its range, and the inverse is a linear map. So that's the statement that we proved previously on page 199. Okay, so, our goal is, where a linear H has an inverse, to find the relationship between the matrices. Now we know if we have a linear map, we can represent it with respect to bases in the domain and the codomain. Now if we want a representation of the inverse, then the domain of the original function becomes the codomain of the inverse function and vice versa. So if we want to represent H inverse, we're going to have to switch the bases of representation. All right, so let's define a matrix inverse. A matrix G is a left inverse matrix of the matrix H if GH is the identity matrix. So GH is equal to I. It's a right inverse if HG is the identity. A matrix H with a two-sided inverse is an invertible matrix. That two-sided inverse is denoted by H inverse. Okay, some examples. Here's a matrix H, 2, 5, 1, 3. You can compute that the inverse is this. You possibly already know the formula for the inverse of a 2 by 2 matrix. In order to verify that this matrix is the inverse, you multiply this times this and get the identity. And that shows that it's a left inverse. And then you multiply this times this and get the identity. And that shows it's a right inverse. So here's one verification The other is also easy. Now here's an arrow diagram that represents matrix inverses. Okay, so here if I have a vector space V, and I'm representing that with respect to the basis B, and I have a linear mapping from V to another vector space W, which is represented with respect to the basis C, and the linear map is H, and the matrix representation with respect to bases B and C is given by big H. I can also define the inverse mapping of this linear mapping, H inverse, and that's going from W, represented according to the basis C, back to V according to the matrix B, the basis B, rather. H inverse is the matrix associated with basis C and basis B. And if these linear functions, little h and H inverse, are truly inverses, then the composition of these two will be the identity. And the product of the associated matrices will be the identity matrix. So here we have H first and then H inverse. Actually, this represents the product H inverse times H. So this expresses the fact that H inverse is a left inverse, of H. That's what's expressed by this diagram. Okay. Now you could do a similar diagram for right inverse, which I didn't happen to do, but that you would simply reverse you'd simply have W here and V here, just exchange those, and you'd exchange this arrow with this arrow. Now, if a matrix has both a left inverse and a right inverse, then the two must be equal. And the proof, in the theorem, a matrix is invertible if and only it's non-singular. And recall the definition of non-singular. Here's the definition right here. Square matrix is non-singular if it is the matrix of coefficients of a homogeneous system with a unique solution. It's singular otherwise. Okay, so let's go on and see the proof. Sorry. Okay. So given a matrix H, fixed spaces of appropriate dimension for the domain and codomain, and fixed bases for these spaces. Okay, with respect to these bases, H represents a map, little h. These statements are true about the map, and therefore they're true about the matrix. So what's going on here? For a map, if a function or mapping, if a function has both left and right inverse, then the two must be equal. Okay? That's a fact that can be proved. Let's see if we can do that right now. Well, suppose that f has a right inverse. Let's see. Let's suppose that f has a right inverse. That would be that f times fr is the identity. And suppose f has a left inverse. That would mean that fl times f is the identity. And we want to show that fl equals fr. So the question is fl equal to fr? Okay. So we can actually multiply both sides of this equation by FL, and we get FL. Now remember, this is composition. Let me make that clear. This is composition. So we can take FL composed F composed FR is equal to FL. Okay. Now what I can do here is I can, since composition is associative, I can write this as FL composed F composed FR. So this here is equal to this is equal to FL composed F composed FR, but FL composed F is equal to I composed FR, and that's equal to FR. So that means that these two are equal to these two are equal, And that means that these two must be equal. So in fact, if a mapping has a left inverse and a right inverse, they must be the same. Okay, so that's the first statement that's true. The lemma is true for mappings, and therefore they're true for the matrices associated with the mapping. Okay. On the other hand, a matrix is invertible if and only if it's non-singular. That's true for mappings. We can look here. Okay. Non-singular non-singular mapping is one-to-one and onto. So a matrix is invertible if and only if it's non-singular. And here we have this lemma that says a non-singular linear map is represented by a square matrix. The square matrix represents a non-singular map if and only if it's a non-singular matrix. Okay, so that means any statement that we make about non-singular maps also applies to the matrix associated with that non-singular map, because that must be a non-singular matrix. Okay, so if a mapping is invertible if and only if it's non-singular, then the associated matrix is also invertible if and only if it's non-singular. Okay, so we have invertibility and non-singularity of matrices are intertwined, and if a matrix has a two-sided inverse, then both inverses are equal. Okay. Another lemma, a product of invertible matrices is invertible. If G and H are invertible and GH is defined, then GH is invertible, and GH inverse equals H inverse G inverse. The proof, because the two matrices are invertible, they're square, and because their product is defined, they must be both n by n. They must be the same size. Okay. Fix the space and bases, say Rn with standard basis, to get maps G and H that are associated with the matrices. Okay. So I can take these matrices and create linear maps that are associated. Now let's work with the mappings. Consider H inverse G inverse. Now, by the prior paragraph, this composition is defined. The map is a two-sided inverse of GH. By this computation, if you take H inverse G inverse times GH, you can reassociate the products so that here, instead of multiplying H inverse G inverse first, you multiply G inverse G first, which gives you the identity. So the identity collapses and gives you H inverse H, which gives you the identity. And this shows that H inverse G inverse is a left inverse of GH. Similarly, we can show that H inverse G inverse is a right inverse of GH by associating the H inverse multiplication first. Okay. So this statement that GH inverse equals H inverse G inverse is true if G and H are functions, and these functions are associated with the matrix G and H, so we can carry over the same statement to the matrices associated with these functions. Okay, so we're proving things about functions and carrying them over to the matrices corresponding to these functions. Another lemma. A matrix H is invertible if and only if it can be written as the product of elementary reduction matrices. We can compute the inverse by applying to the identity matrix the same row steps in the same order that Gauss Jordan reduce H. The proof, H is invertible if and only if it's non-singular, and thus the Gauss Jordan reduces to the identity. Remember that if we have a non-singular matrix, we can reduce it to the identity. Now remember, the Gauss Jordan reduction steps can be associated with products by elementary matrices. So every time we do a Gauss Jordan reduction, we can associate that with a elementary matrix. So my first reduction is associated with the matrix R1, second with R2, and so on down the line. Okay. Now, so here we have that this product of reduction matrices times H is equal to the identity matrix. Okay. So for the first sentence of the result, note that the elementary matrices are invertible because elementary row operations are reversible. And their inverses are also elementary. If I apply RR inverse from the left to both sides of star, then apply R negative inverse, etc., the result gives H as a product of elementary matrices. H equals R1 inverse blah, blah, blah times RR inverse times I. Okay, so what he's saying here is that I have this equation here. If I want H by itself on the left-hand side, I just invert these matrices one by one. I multiply here by RR inverse. And here I'd multiply also on the left by RR inverse. Then I multiply by RR minus 1 inverse. And then same thing here, I'd multiply this on the left by RR minus 1 inverse. In the end, you'd end up with this expression here. And you get H as a product of elementary matrices. Okay. Now, for the second sentence, let's group star in this way. And here we have the fact that this here is a left inverse of H. Okay. The fact that this product of elementary matrices is also a right inverse of H can be found by looking at this representation of H. If I take this representation of H and multiply on the right by this sequence of elementary matrices, you can see that the product of those two will give me the identity again. So in fact, this product of elementary matrices is both a left and a right inverse. And here's an example of a matrix that's non-singular, and so it's invertible. To do the inverse calculation, one way to do that is to write the matrix and write the identity matrix next to it. Now, when we apply row operations, we apply row operations both to the original matrix and to the identity matrix. And the row operation applied to the identity matrix exactly gives the elementary matrix associated with the row operation. So as we go through step by step and apply elementary row operations to both the original matrix and the identity matrix, we are getting the product of elementary matrices that is inverting the original matrix. Okay. So we have to keep on reducing until the original matrix reduces to the identity, and then what's left on the right-hand side of the bar will be the inverse of that non-singular matrix. All right, so we reduce to here, and you can verify by multiplication that this is actually the inverse of the original matrix that was given. All right, so finding the inverse of a matrix is a lot of work, but once we found it, then solving a linear system AX equals B is easy. Consider the following linear system, which can be expressed as a matrix equation. All right, see 1, 3, 1, that's the first row here, 2, 0, minus 1, second row here, etc. Now I can take this matrix equation and multiply on left and right by the inverse of this matrix A. If I multiply on the left, I multiply this matrix on the left by the inverse matrix, I get the identity. What's left on the left-hand side of the equation is simply XYZ. Now, since I've multiplied here on the left by the inverse, I have to multiply here on the left by the inverse. But I can do that by straight matrix vector multiplication, which gives me this result. So in fact, this is the solution to my original system of equations. For a 2 by 2 matrix, there's this standard formula. And the best way to prove this is just simply verify that this matrix times this matrix gives you the identity, and also this matrix times this matrix gives you the identity. Here's some examples. The 3 by 3 formula is much more complicated, and I think that's all for this presentation.